let's take a look at how we could answer the same questions here with technology. So the first thing was just simply to graph the function given, which of course in Desmos here that's super simple. And I've made this tool for you to use actually in other exercises later that you'll do that you can use. And you can replace this function with other functions and it'll be very helpful. The second part of the questions that were asked of us was to find the equation for the secant line. And actually I've put a folder here with the mechanics of what I've set up, because you can see that I have the graph of the function in orange and then the secant line here between -2 and 3. Those are the x values asked of us. And if we look at the mechanics, hopefully you can make sense of this. M is slope. You can see this is difference in outputs over difference in inputs. And that's for my b and a, right? So f of b minus f of a over b minus a. And we can see that this is 27 as I've set these values. So we found it correctly. And just to remember, we use point slope form often. And so I've put that with this m value. And I've just built this point slope form specifically around the a coordinate. It would have still worked if I put f of b and x minus b here as well. Okay, so just make sure you kind of understood that. So that is essentially how I answered that part of the question, finding the equation for the secant line. Slope is 27, and of course, if you want, you can look -18 as the intercept, so you can build the slope-intercept form off of this. And the last part was finding the third intersection. So if you notice right here is where that third intersection point is, and again, Desmos nicely finds intersection points automatically for us, and we were also correct there. So one thing that you'll be asked to think about here, because it really relates to calculus, is answering the question, what happens as these 2 points move closer together to each other, as we've also talked about in the recent past. And what we can do is if you leave A alone, you can actually play with this secant line, and it's going to stay there, but you can bring the B value closer and closer to A, or you could have brought A closer to B from the other side. And we're kind of taking a look at the slope as we move it. And if we actually open this back up again, you can see that when we move this, the slope will continue to be calculated for us as we move it around. So there's how we can use this Desmos file to help answer the questions that we've been working on.
Remember, the main goal of today is to be able to find the equation of a secant line that connects 2 points on a polynomial graph. So far we've used algebraic methods. We've also looked at how we can use Desmos to find this, but we want to start thinking about calculus. So we're going to look ahead to calculus again to end off today's lesson. We need to remember the remainder theorem to help us with this, and everything we've been doing is actually building up to this. So again, let's look at the function from example 3, and we want to know what the remainder is when we divide by x plus 1. So to remember the remainder theorem gives us a nice shortcut to find the remainder when I divide a polynomial by a linear factor without having to actually do the whole long division process. Let's remind ourselves of this. So the first important fact to remember here is that remember that if x plus 1 is a factor, if it was to be a factor, it turns out it's not here, but that would mean that x equals -1 is a root, and we've been talking about that lately. And again, that means that f of -1 equals 0, right? If it's a root, that x-intercept, right? But this 0 also stands for the remainder if we divide it, right? If it evenly divides, that means the remainder is 0. So the cool thing is, the remainder theorem says even if it's not divisible, if you plug -1 in, it still gives the remainder. So this can be used to answer this question. So long story short, if I want to know the remainder when I divide by x plus 1, then I can just plug in -1 and see what the remainder is. It'll tell us if it's divisible. If the remainder is 0, that means x plus 1 divides evenly. The remainder here is not 0, it's 16. That means x plus 1 does not divide evenly, which is totally okay, but this can be helpful, actually, to find the equation of a secant line. There's a little bit more to remind ourselves about the remainder theorem before we push on. And it has to do with how we rewrite a function once we've done the division. So obviously we just found that if we did the division, 16 would be my remainder. We'd get some function, some other function, plus 16 out of x plus 1, right? Just like when we do regular division, this is like the leftovers fraction. Well, I did the work and I found that that something actually is 2x squared minus 2x minus 16. But remember, there's a way more useful form for this. I'm going to multiply x plus 1 onto both sides here. You'll notice this x plus 1 cancels out with this, but it then needs to multiply here. So what I get is the original function on the left, and whatever's over here must just be a rewritten form of that function, of course, right? So I get x plus 1 times my quotient plus 16. And this is really helpful because this actually shows me, remember if this is f of x, this shows me an easy way to calculate f of negative 1. Because when I plug negative 1 into this, it makes 0, and all that collapses and gives me 16, just like I thought. This means as a general rule, any function, polynomial function, divided by some linear factor x minus a, you get the quotient, and then you get your remainder over x minus a. But that can always be rewritten in this way to help us show that, of course, f of a equals whatever's left there, which is f of a. Now, rewriting in that way is going to be very important as we move on. Now we're at what we've all been waiting for, I'm sure. The same function that we just have been looking at. Find the equation of the secant between these 2 points. Exactly the same question that we asked previously, but let's use the remainder theorem. So, as we just saw a moment ago, we can rewrite f of x as x plus 1 times this polynomial when we divide it, plus that remainder of 16, right? Now, technically this 16, just to show you a pattern, that was f of negative 1, right? Based on the remainder theorem. Now, if we rearrange this equation and subtract this over here to make f of x minus f of negative 1, and then afterwards we divide by x plus 1, but technically x plus 1, right? Isn't that x minus negative 1? Then we get 2x squared minus 2x minus 16, right? But writing it this way should look really familiar. This is actually the slope formula, because it's the difference in y over the difference in x. But specifically the slope from negative 1 to any other point I want, actually. So here's the crazy thing. This equation right here is actually a formula for the slope from negative 1 to any other point on that curve that I want. That's really, really powerful. Let's use this to solve this, because the other x value that I want to plug in here would be 3. So this equation right there will always give me the secant slope from negative 1 to another point. Our point is 3. So if I plug in 3, all I have to do is plug it into here, and it'll give me the slope of the secant. And that's going to be, if you do this calculation, negative 4. Exactly what we found before. This is quick and really powerful. And so our final equation, easiest way is to use point-slope form now that we know the slope. Well, we already wrote these down before, but we'll write it again. Y minus 16 equals negative 4 times x plus 1, or y minus 0 equals negative 4 times x minus 3, which the 0, of course, you can leave out if you want. And there we go. All right, folks, home stretch. Last thing for this lesson. Repeat the same exact instructions from number 6, except we're going to use our function from problem 4, and then the same exact 2 points for the secant line there. And I've given you a little bit of a head start, so it's less work for you. We're going to use this point, and so the factor would be x plus 2, and we know the remainder would be negative 72 at the end. And I did the long division for you to get this. So remember to rearrange this equation so it looks like slope, and then just answer it the way we just did, and we'll check. So your rearrangement should look like this. Here's the slope, and it's equal to this piece I got when I divided right there. And it turns out that formula is a formula for the secant slope. Well, kind of like the last one, kind of coincidental, but 3 is the x value I want to find the secant line of from negative 2. So again, the secant slope would be this. And if we plug in 3, our slope is 27, just like we got before. And so either this point-slope form built on that point, or else this one will both be correct answers to find the equation for the secant line. How nice! This concludes our lesson for today. So again, happy math, and we'll see you next time.